In this tutorial, we'll see how we can produce the relevant plots to help us assess whether the regression assumptions are met. So as usual, be sure to download the corresponding PDF file and our script associated with this tutorial. We've kind of explained, right, that we use scatter plots, ACF plots, and a normal probability plot to help us assess the various regression assumptions. So in this tutorial, we'll be using this data set called windmill. It's basically the data reflects the DC output from the windmill and the corresponding wind velocity from a researcher. So we'll just read that data set in as usual. If you actually open up the text file, the first row represents the headings associated with the columns. So we'll have to put header equals true. I'll attach the data and I'll fit a linear model for so the response variable is the DC output and the explanatory variable is the wind velocity. So let me just read all of that in. So one of the things we say, right, we can produce a scatter plot to see if the regression assumptions are met. So the way we can do this is I'm going to just create a scatter plot, X variable, Y variable, and I'm going to put a title for this. And one thing that could be useful is actually to overlay the least squares line on the scatter plot, right? So I've already created the least squares regression. So let me just create the plot as usual. So that's my plot. I can overlay the least squares regression line by using the AB line function, right? Result is my linear model. And I'm going to put this in red to kind of distinguish that from the plots, right? So that's the least squares regression line. So a few things we can look out for over here. We know that as one goes from left to right, the data points should be evenly scattered on both sides of the regression line. So we notice that for a low wind velocity and high wind velocity, the data points tend to be on the lower half of the line, whereas the wind velocity in the middle range tends to be on the upper half. So this kind of indicates that we don't have a straight line relationship, right? It kind of looks like a curve over here. So we already see that, at least one of the assumptions is not met, i.e., right, we don't have a linear relationship. The vertical spread seems fairly constant, so I'm not so concerned with that one, but really we can kind of see one of the assumptions is not met, right? And kind of a byproduct of the fact that this is a nonlinear relationship is the fact that the average value of the residuals, as one moves from left to right, they are not zero, right? The residuals will be negative here, right? The residuals here will be positive and the residuals here will be negative. So that's one thing you could use. One of the things I've always said that a scatter plot only works if you have just one predictor variable. So normally most of the time you'll be using a residual plot. So residual plot has the y hat, the fitted values on the x-axis, and the residuals on the y-axis. So that's what I'm putting inside this plot. And I'm going to overlay the horizontal axis in red. So let me just plot this, and that's my residual plot, right? So this is the horizontal axis, and again, what we're looking for is whether there's any pattern. So we notice there's a curve here, which is reflective of what we saw in the scatter plot. So already, that's not great. The other thing we also want to look for is that the residuals are evenly scattered on the horizontal line, and we can kind of see these are all negative, these are all positive, and these are all negative. So already that's not met. The vertical spread seems fairly constant, right? The vertical spread of the residuals seem fine. So again, right, we need all of these features to be met, right? In this case, some of the features are already not met. So we already suspect something's not quite right with this data set, or at least with this linear model. Some other things could do just to complete the checking, right? Check the independence of the error terms. We use an ACF plot. So that's the ACF plot, and again, for all lags 1 or greater, they should be insignificant. So the blue line represents a significant correlation between certain lag. So they're all uncorrelated. So this assumption is fine. The last one we could check is the normal probability plot of the residuals. Some people call it a QQ plot. So to produce the normal probability plot is using the QQ norm function, and you're putting in the residuals in it. It's very useful to overlay a line that represents the expected value based on the normality assumption. So we use the QQ line function for that. I'm going to use the red red to represent this QQ, this line over here, just to distinguish things. So ideally, right, if the residuals follow a normal distribution, these plots should be on the straight line. This normality assumption, as I've said, is the least crucial assumption, but just to be complete, we will check for it. So we've really kind of seen, right, that of the assumptions that we have, the assumption about a linear relationship, right, that's the questionable one. The constant variance assumption seems fine, right? So in that case, if the linearity assumption is the one that's not met, then we consider typically transforming, I should say, the x variable. Right, so we can transform the x variable based on what we see. So one possibility is use the inverse function where we kind of saw that curved relationship. So maybe using an inverse, right, raising the power, the x variable by the power of -1, that could work. So let's try that transformation and let's fit a new linear model with the transformed version of my predictor variable. So I'm going to create a plot. I'm going to split my plotting device into a 2x2 matrix because I'm producing the scatter plot, the residual plot, the ACF plot, and the normal probability plot. So I'm going to produce all of these for this model which uses the transformed predictor variable. So let me just produce all of this, expand this. So again, for the scatter plot, right, we want to see whether we have a straight line relationship. That seems fine. Vertical spread seems fine as well. The plots are on both sides of the regression line as well, so that seems fine. We can kind of check that using a residual plot as well, right? Are the data points evenly scattered on both sides of the horizontal line? That seems fine. Vertical spread seems decent, right? And we don't really notice any curved pattern associated with the residual, so it looks like this transformation works. Looking at the ACF, right, these are all insignificant for lags 1 and greater. QQ plot, again, is not perfect, right, but it's the least important assumption. So we are more bothered really with the residual plot and the ACF plot really. So this seems fine. We seem happy with that, right? And basically, if we wanted to carry out our analysis, right, then we are basically using this model using the transform predictor. Okay, so we're going to close the plotting device and going to now look at how we could use the Box-Cox transformation. So we already transformed the predictor variable, but what happens if we want to consider transforming the y variable? So we consider transforming the y variable when the variance is not constant, and it's found in the mass package. So the Box-Cox function is found in this mass package, which is not part of the standard or default R package. So we're actually going to have to install this package. So to install a new package, click on package and select install packages. And you'll see a bunch of mirrors being populated, and you should choose the one that is closest to you. So given that I'm in Virginia, so North Carolina is probably the closest one, and click on OK. And you can see all the packages that you could install, and it's all in alphabetical order. So I'm just going to scroll down all the way to MASS. So there are a lot of packages because a lot of people use it and they upload their own. So click on mass, and to install it, click on OK. Now I already have this package installed, so I'm not going to click on OK, but you should do that on your own. So for myself, since I already have it installed, I'm just going to cancel out of there. I just wanted to show you how to do it. And if you already have a package installed, you can just type in library and then the name of your package. And that will load that package, and any function associated with that package will be loaded, and you can start using them. So the Box-Cox transformation is via the Box-Cox function. So now that I've already loaded the mass package, I could perform the Box-Cox transformation on my current model, right, to see if I need to transform the y variable. So I perform that function, and this is the profile log likelihood that's provided to me, and I'm focused on these 3 vertical lines. It gives us the value of lambda that is the best for the transformation. what I want to look at, right, is these three vertical lines. So the middle one gives us the value of lambda that is the best, and the lower and upper bounds of a 95% confidence intervals are also given to us. Strictly speaking, right, what we want is a value within that range. You will also notice that by default, R will produce lambdas between -2 and 2, and what we have are lambdas that are around 1. So maybe you want to rescale the x-axis, and so to do that, we could use specify lambda equals to whatever value. So SEQ means sequence. I want it from between from 0.6 to 1.6 in increments of 0.01. And basically, if I run this code, right, this produces the same graph, but with lambda from 0.6 to 1.6. So I can kind of have a better idea about what these values are for the lambda, right? So again, the middle one is the best, but any value within the upper and lower bounds of your confidence interval will be fine. And usually what we want to focus on is whether 1 is inside the interval, because if 1's inside the interval, it means, right, raising our response to the power 1 is reasonable, right? And raising something to the power of 1 is basically saying you're not changing it. So this kind of informs us that we don't have to change or transform the response variable, and it kind of makes sense from the residual plot earlier on. I kind of made a comment that the um, uh, constant variance assumption seems met, and 1 is within our 95% confidence interval, right? So that's fine, and it kind of does match up with what I kind of suspected. So this should generally match up with what you see visually, right? So visually we said doesn't seem to be a need to transform the variable, and we notice that 1's inside the interval. So yeah, so that's basically how we could use the Box-Cox transformation